The world population will reach 9.8 billion by 2050, meaning that global food production must rise by 70% to keep up with demand. Revolutionising agricultural farming is intrinsic to sustaining food stock while significantly reducing its impact on the environment. Wheat is the most commonly grown crop, with an estimated 736 million tonnes harvested each year. Farming currently accounts for 13% of global CO2 emissions. Heavy machinery also leads to soil compaction, hindering root growth and nutrient absorption. Meanwhile, chemicals used in excess can run off into rivers, destroying the biological ecosystem of the surrounding area. Herbicides are often added to minimise crop losses from diseases like wheat leaf rust, which can result in a yield loss of up to 30%. It was important to create a solution that could tackle these problems. The aim was to design a group of agri-robots to monitor the health of cereal crops via onboard sensors. 2 robots had to be designed. A small 10 cm wide autonomous crop inspection robot to go down narrow crop channels, and a higher level mother robot to facilitate communication and charging of the small robot. Key subsystems were identified and current solutions and literature were researched.
The small robot platform had to secure all components, whilst being no more than 10 cm in width. A 3-tiered chassis design was adopted. The batteries were placed on the lowermost level to ensure a low centre of mass. The mother robot's geometry allows for the housing and shielding of 2 small robots from the elements. Both robots are driven by DC motor differential drives. They have a ground clearance of at least 3.75 cm, allowing them to go over any undulations in the field.
The robots had to have the computational ability to sense the environment and autonomously localize and navigate within it. To carry out these tasks concurrently, a master-slave setup using the Raspberry Pi and TNC microcontroller was used. The bottom layer contains the main controller board that's responsible for the low-level control of the robot. Here, you can see the small robot reversing into the charging pads, which were offset from one another for electrical protection.
A bespoke time-of-flight sensor array was designed for close-range sensing of obstacles. This was useful not only for probabilistic mapping, but for map-based localization. Building a map of the environment allows a small robot to operate in any field. A map is generated by driving the robot around the environment and building an occupancy grid. This is key to enabling autonomous navigation.
Localization gives the robot awareness of its pose in the environment. When a map of the environment is available and the robot can localize itself based on the map, it can autonomously navigate in the farm field based on set points generated from coverage planning.
Wireless communication is key to enabling remote environment sensing and coordination between the 2 robots. A scalable 433 MHz mesh network allows distributed data sharing and increases network coverage in the field. When charging, a data offload takes place over a 2.4 GHz wireless local area network access point so that data can be stored and post-processed by a central base station server.
Many diseases change the colour of the leaves, which allows for their detection via RGB thresholding. By normalizing the brightness of captured images, a consistent colour range can be achieved. Then, by applying an RGB filter, rust can be detected under different lighting conditions. Multiple filters were used to capture all colour variants of the disease. Detecting rust at an early stage can avoid large yield losses.
Environmental sensors help to give an indirect indicator of crop health. Environmental parameters, such as temperature, humidity, and light intensity, are acquired on a site-specific basis. These can be spatially plotted in order to visualize intra-field parameters.
To conclude, the project has achieved a platform that provides a proof of concept for crop inspection on a small robotic level. The robots navigate through the fields using simultaneous localization and mapping, path planning and obstacle avoidance. Sensors distributed throughout the field can collect environmental data and transfer them to a base station for post-processing. Future work for the project includes implementing autonomous navigation on all robots. The mother robot must be fully autonomous for the transportation of the small robots between fields. In addition, neural networks and machine learning can aid in disease detection and classification. To further expand the robot's precision farming capability, a method of chemical application could be developed.